Hello, it's Keith here, and this is lesson 68 of the platform-specific series of my Z80 assembly programming tutorials, and we're on the Amstrad CPC once again because the Amstrad CPC is the system I grew up with, so I enjoy playing with it. It's the first one I always go to. Now, today we're going to be looking at overscan and drawing graphics on the screen and a very crude way of compressing graphics in a lossless method. Now, I was doing this kind of experimentation, and the follow-on for this was actually the quad tree video compression that I used for my 10K subs video. Now, if you want video compression and you want a lossy compression, that would be the one I would use. However, if you want lossless, very high quality compression, this is an interesting one, and this was really me playing around with trying to improve the efficiency of an existing compression technique just by slightly altering the way I used it. Now, we've got this nice big CPC image here, and if we were to save this as a raw file, then this would actually be a massive 27 kilobytes here. So this is quite a big file. If we were, let's say we got a game, we wanted multiple images in memory or to load them from disk, this is going to be a very, very serious problem with this file size. Now, I've played with in the past a simple RLE compression routine, which I actually nicked from a Sega Master System game, ironically. But if we were to compress this image in a very simple way, just as a normal file, this would compress this down to 14 kilobytes. Now, what I thought is, well, maybe if we're a bit more intelligent about the way we compress the file and we make some assumptions about the kind of data, maybe we could compress it a little bit more. And so what I've done is I've split it into bit planes, and I've actually worked within 8x8 pixel blocks. So effectively working with this kind of like a Game Boy tile map. And then I've exported the file as two separate bit planes. And if we combine these two together, these are actually much smaller. And if we just go over here, I've actually got the calculations on screen here. So the original file would be 27278 uncompressed. We can compress it down to 13425 using RLE, but if we split the bit planes and work in 8x8 blocks, this will only be 11,144, and we're saving 2,281 over the simple RLE compressed data. Now, the reason I'm using bit planes and compressing in 8x8 pixel blocks is I'm making some assumptions. Now, an area like this that's dark blue, this will have no data in bit plane 1. This is only using bit plane 0. And because the CPC clusters 4 consecutive pixels into a single byte, working horizontally across the screen, it's often going to sort of come across bytes that are different. Whereas going down and working in 8x8 pixel chunks, you'll see there's small areas that are solid blue here within an 8x8 pixel block possibly, but consecutive pixels are all going to be different. And you see there's little blocks of black here and there and things like that. And I thought that working in these 8x8 pixel blocks would be more efficient. And it certainly saved a little bit of memory. As I say, this was really just an experiment into seeing about to what extent making assumptions about the kind of data would allow me to compress the file without coming up with any ridiculously complex compression techniques, which ironically the quad tree video was a more ridiculous compression technique. But anyway, as I say, this is what I've come up with, and so here is the source image. You can see it's in Acrosprite editor. And so to export this for today's example, what you would need to do is rather strangely use the Game Boy option, because as I say, we're basically compressing in bit planes in 8x8 pixel blocks here. So you would use this save raw bitmap option to save the raw file, and then you would want to compress that using the file processor here, and you would want to use RLE compress split alternating bytes, and this will effectively split the two bit planes into two separate files. And that will produce the data that you can see here, overscan RLE1 and overscan RLE2 here. And those are the files that today's example is going to use. Okay, so let's go over to the source code and let's see how we actually get this into memory. So we've got our two files, here they are, the test image here, and we've got our two RLE bit streams here. Now we've also got our CRTC values here. These are the settings for the screen. I recently covered the overscan format in the simple series, so if you want to see more overscan, please see that. We've also got our palette in hardware format here. We're disabling interrupt here, and we're going to do everything ourselves. So the first thing we're doing here is we're starting at memory address 100, and we're setting the stack pointer to 8200. Now the screen in overscan, we're going from 8200 to FFFF, so this is basically going to use some of that spare memory there. And then what we're doing here is we're transferring the palette to the hardware. We're using the hardware, we're not using the we're not using the operating system at all. And then we're using palette entry 16, which is the border, and we're setting the border to black here. So that has defined the entire palette, including the border. What we're doing next is we're transferring the CRTC values to the hardware. This is setting up our screen. And then what we're doing here is we're effectively clearing the screen. We're setting all of the bytes to 0 to start with. Now, these routines are both using XOR here. So this is assuming the screen is going to be blank to start with. Now, you could do this in a different way if you wanted, but as I say, that's what I'm doing here. Now, before we look at those screen transfer routines, let's look at our RLE decompressor. Now, this is, in the past I've used this RLE technique and I've written the routine around it. This is more of a generic RLE decompressor, and we can request single bytes from this. So this is slower, but it's much more flexible and much more useful for if you're just getting started testing, I guess. And if you really want to squeeze all of the performance out, you would want to sort of unwrap, if you will, the RLE decompressor into your code. But this is a very simple one. So to use this one, all we do is we load the source data into IY, test image in this case, and then we run RLE decompress to start things up. We then read in our source data, 1 byte from IY. We then run RLE get next byte to read in the next byte. Now, the RLE decompressor is very simple. Basically, it will have a parameter byte, and that byte will have a top bit of 1 if the data is RLE, and a top bit of 0 if the data is linear. Now, linear data is random data that wouldn't compress, and RLE data is a single byte repeated up to 127 times. Now, a byte of 0 is actually the end of the file stream. Now, in the case of a byte of 0, we're going to load IX with 65535. If that's not the case, what we're basically going to do is we're going to load IH with the number of linear bytes, the number of uncompressed bytes, or IL with the number of RLE bytes, which will all be the same value in IY. Now, if you were going to unwrap this code, what you would then do is process those loop counters within your code, and you wouldn't keep going back to this generic routine. But for today, we're using a super dumb routine, and we're just repeatedly jumping back to RLE get next byte. And what this is doing is checking IXL, and if IXL is 0, then it's not an RLE. That should be an N, not an M. There's a typo there. That should be not RLE. If IXL is non-zero, though, this is our RLE data. Otherwise, it is linear data. So we're decreasing IXH and moving through the source data stream in IY. Now, if IXH or IXL reach 0, then we need to read in the next byte from the source stream and process that accordingly. So that's how we're getting our RLE data and processing it. Now, how are we actually getting our image to the screen? Well, our screen starts at 8200, and what we're basically going to do is we're going to read in a byte from the source stream, and we're going to transfer it first to bitplane 0, the first image to bitplane 0, and the second bitplane to bitplane 1. Now, the CPC screen in mode 1, the top 4 bits are bitplane 0, and the bottom 4 bits are bitplane 1. And so what we're going to do is we're going to read a byte in from our source twice, and the first time we're going to take the top 4 bits, and then the second time we're going to shift the bottom 4 bits to the top 4 bits and mask them accordingly. And we're going to XOR that with the screen data. Now, for 7 lines of the screen, we can just add 8 to the H part of the HL pair to update our VRAM destination. But on the 8th one, it's a little bit more tricky. What we're going to have to do is we're going to have to add hexadecimal 60 to the L part and update the H part accordingly. But there is a bit of an issue here because there is actually a gap between the two VRAM banks within this this super large overscan screen, and so we're doing a check here, and if we're actually at the end of the first bank, we're manually wrapping into the second one here so that we are into the C000 bank here, and so that is allowing us to sort of cope with those two banks there. Now, this has done bitplane 0, but then we need to do the whole thing again for bitplane 1. Now, this time we're doing the bit shift on the first byte, and we're masking the bottom 4 bits, and then we're doing it on the second byte, and we're again masking the bottom 4 bits. These two routines are basically identical with the exception of the mask and the position of the bit shift. So they're the exact same sequence here. Now, I could have written a more generic routine and used one routine to do both, but I thought for simplicity, to make it clear what's going on, I thought I would separate them out here. But as I say, I thought this was quite an interesting little experiment in just to see what we could do. Firstly, playing with BitPlanes on the Amstrad CPC, and to see how we could optimize RLE compression by changing our drawing routine and doing things differently. As I say, this is intended for a game like a point-and-click adventure or something, where you want to be able to show big, high-res, high-quality images, and speed isn't a priority. If speed is a priority, or you want efficiency, my quad tree compressor, I say in the 10K subs video, is more suited. Anyway, that is all we have today. If you like what we've seen, please like and subscribe as always. And if you don't know about it, I've written a book and you can buy my book to support my channel. It's a Z80 programming book. It covers Z80, 6502, 68086, and ARM. So if you want that, please take a look on Amazon. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching and goodbye.